Hello everyone, this is video 11.1. We're going to be looking at concepts of measurement. So what does it mean to measure something? Why would we need to measure something? What are the units by which we measure things? So looking at all these ideas in chapter 11, specifically looking at some basic ideas so we can kind of set the stage for some of the other sections that are going to be coming shortly. So let's get started. So this idea of which is bigger, um, it's a sort of thing that I think a lot of kiddos are really interested in asking and wondering. The idea of the biggest animal or the biggest planet or the biggest whatever. Things that are the biggest. It's a pretty cool idea. The problem is like how do we understand what we mean by bigger? Um, so if we think about the IDS Tower in downtown Minneapolis, we know that it's taller than US Bank Stadium, where the Vikings play, but US Bank Stadium is certainly bigger around at the bottom. And so, are we talking about height? Are we talking about the distance around? Are we talking about how much it could hold? Um, so, it's hard to really compare what we mean by bigger without having some sort of consensus, some sort of consistent idea of what we mean by bigger. And so this is one of the things we're going to be looking at in this section. How do we define these dimensions? How do we compare these dimensions? How do we measure these dimensions? So we can come to a pretty uniform way of talking about what is bigger. So before we get into measuring, sort of the prelude to this is just the idea of comparison, which really is a sense of measurement. It's measurement without number. We just know that this one is shorter, this one is longer, this one is taller, this one, whatever. So we kind of like look at two things and we know that one is bigger by some agreed upon dimension. So when I was looking for examples of this, I like this little chart that this class made, where it looks like students made little worms, and it looks like they sort of squiggled out their worm. This is probably related to some book that they read, and you can see that they put little eyes and drawn little segments on the worms. But everyone made a worm, and so now we can compare. Well, this worm is longer than this worm, and this worm is longer than this worm, and so those pairwise comparisons, so just taking a pair of worms and comparing which one is bigger, now we start to order them into longest to shortest. And then we have this little arrow here for which one is the absolute shortest. This is a cute little worm there. So, this idea now of getting an idea of comparison leads us into measurement. Now we know this one is the shortest, but by how much? And this one is the longest, and the longest by how much? It's a very natural question, but before we get into that question of sort of quantifying uh, length or area or whatever dimension we're going to be looking at, and we're using length here because it's a good starting point. We're just measuring along one dimension. So as the prelude to measurement, we're just looking at comparing, and then that like I said, that natural question of by how much that leads us into measurement. So we need to define some terms. The first one is the idea of a unit, and so a unit is, it says here, a fixed amount used for measuring. So we need to know that what we're going to be using for measuring is going to be consistent. If an inch changed from day to day, or if an inch changed from person to person, it wouldn't be very good as a unit of measure, because then an inch for one person, an inch for a different person, there's no consistency in measurement. And you can see how this would be the same thing no matter what unit we're talking about. If miles were different from state to state, then knowing how long it takes to drive a distance, we couldn't possibly know if that unit wasn't standardized. So it needs to become fixed, and then we all have an understanding and an agreement of, okay, I know what that unit is. Now, measuring is the act of comparing something to that fixed unit. So now, once I know what a mile is, and I have two places in mind, I want to drive from Minneapolis to Duluth. Well, now I can use that unit, that mile, to measure off how many miles are there from here to there. And now I've measured, I've used that unit to create a number that tells me how many of those units exist from here to there. So that's what we mean by measuring. So one really common way, and this is a great activity to do with a class when you're getting into measurement, is to start with something that's called a non-standard unit of measurement. And so you can see there's some examples there on there, like a hand span. So the distance from one thumb to one pinky. And so you can get students to sort of measure how many hand spans it is from one edge of their desk to the other edge of their desk, or to measure a foot. And so sometimes you can take, a student will put a foot on a piece of paper and you try to trace around the foot. And it gets to this idea that we need a standardized unit of measurement. You get students measuring their feet and then cutting out those feet from the paper and then using that foot to measure. And so now you might have 3 or 4 students measure how many feet it is uh, to go from the bottom to the top of the classroom door. But because the feet are all different lengths, they're going to get different numbers. And so that'll help motivate students to understand why we need standardized units of measurement. And so then we clearly become toward the conversation of, well, this is where the idea of a foot comes from, that people would use their feet to measure distances, but because feet are different sizes, obviously, now we have a standardized foot that's 12 inches. And you can talk about where the inch comes from. A lot of these U.S., which used to be British standard units of measure, have interesting historical aspects to them. And some things like hands. I mean, horses are still measured in hands, but what a hand is has become standardized and codified. We know exactly how many inches a hand is now. But this is a good starting point. This activity when I taught middle school had a student lay down and trace them out of on a piece of paper and then cut that out and then figured out how many of that student it was to go down the hallway. And so you could see it's 5 Charlies across the room. So it's a fun activity, but not only is it fun, like I said, it gets us to the idea of why units need to be standardized. So we have 2 different unit systems that we're going to be looking at. So the first one is the U.S. customary system of inches, ounces, and fluid ounces, and we'll talk about why I've sort of arranged them in that order. And this is the system that's pretty much used throughout the United States and well, only in the United States. Most other countries have come along to the other system here, the metric system, um, which is used pretty much everywhere else. Uh, it's also the metric system is become part of the SI units, which is the international standard for units, and so it's used in a lot of science. So realistically, the more you can get students working with metric is going to help them in their science as well. Um, so it's a weird balance because we interdisciplinarily need to move them into metric, but their comfort may be more with U.S. customary. So it's really doing a little bit of both, but knowing the direction in which we're headed. The metric system uses meters, grams, and liters for the measures of length, of mass, and of capacity. So that's why they're in that order, so we can kind of see the inches to meters and ounces to grams. So they're in that consistent order. There's also these prefixes here, and there's a table in the book that goes to these prefixes. Um, you should know most of these. Some of them come up more often than others. You could probably go, a couple of years at a time without hearing anything about hecto anything, unless you're talking about hectares and farming. But some of these come up certainly more often than others. When I was a kid, the idea of anyone talking about giga anything was pretty rare. But now people know about gigabytes and gigahertz on their telephone. So it's interesting over time these prefixes as things have become both bigger and smaller. We hear more and more and more of these prefixes. But certainly you either need to know these or have this table available to you. So if you see a question about these prefixes, you're able to answer them. So these two systems are not necessarily related. They're developed pretty independently, so it's not like one sort of sprung from the other. Um, there are some rough comparisons that we can make, and we could talk about, about a kilogram's about 2 pounds, or a gallon's about 4 liters, just so students can have an idea of what's going on. Although it's pretty interesting that I think, most students sort of, when we talk about some of these ideas, they have an idea of what these things look like from common usage. Most students, even if they don't feel like they know a lot about metric, they know what 2 liters looks like because they've probably seen a 2 liter bottle of soda at some point. Um, and a water bottle, a lot of water bottles are 1 liter, although they may be using a 500 milliliter or 750 milliliter bottle, but a lot of the bottles that they have seen are 1 liter. So there's some idea of what some of these things look like, but knowing one doesn't necessarily help you understand the better, not in an exact way. They're sort of their own systems, so they sort of need to be learned independently a little bit. Now, one thing that does have a relationship are these idea is the idea of the units of length, area, and volume. So, as an example, the centimeter is a unit of length. So we know how long something is. We measure it out, for example, by centimeters, and we could use meters or kilometers, or whatever. But I'm just using centimeters as an example for this. So, if I wanted to know how far it is across my desk, I can measure that out in centimeters. Now, once I start to measure area, now I want to know the working area of my desk, how much surface area is there. Well, now I would want to measure that out in square centimeters or centimeters squared, whichever way we want to say that or write that. They're both pretty acceptable. So I want to measure that out in square centimeters. And that is exactly what it sounds like. It is a square that is a centimeter by a centimeter. Um, we'll look at the next slide here. Some confusion that can come from that, but it's a 1 centimeter by 1 centimeter squared. Now, if I want to look at the volume, say, of my classroom, now I'm measuring along 3 dimensions. I want to know, the volume. Now I'm measuring that space out in cubes, and each of those cubes would be a centimeter by a centimeter by a centimeter, and that would measure out the volume. But the point is that that unit of length, that centimeter, helps define my area as square centimeters and my volume, my space, as cubic centimeters. So understanding that linear measure becomes necessary for having an idea of what that area measure and that volume measure look like. So this leads us to a really common misconception. So if we look at this cube at the bottom, and picked a Rubik's cube because it helps sort of illustrate the picture that we're looking for. So we know that each one of these edges, and I'll draw what I mean by the edge here. So you can see along the side, this is 1, 2, 3 centimeters. So this is 3 centimeters from here to here. We'll take each one of these little notches as a unit. So this is 3 centimeters. So then if I measure along here, this is also 3 centimeters. And so it's really common for students to talk about this area, this face of this cube, and they'll say, well, this is 3 centimeters squared. Or they'll say 3 centimeters times 3 centimeters, and then that makes 3 centimeters squared. And so this is correct as far as the units go. This centimeter by centimeter will make this centimeters squared. So that's correct. But what they're not doing is they're not changing the actual quantitative amount. This 3 by 3 is not going to make 3. It should make 9 centimeters squared. And so you can see that's going to happen here on this face as well and this face as well. So students, in my experience, are either so focused on units that they make mistakes with the quantitative aspect, or they're so focused on getting the right number that they sort of forget about the units. And so the other incorrect answer I would really expect here would be 9. So we would say that the area of that face then would be 9 centimeters. Because, well, 3 by 3 is 9, and, well, we're still measuring in centimeters. And now this would be incorrect. So we want the 9 from here and the centimeters squared from here. But both are really common Really, really common mistake. So be looking for that. If your natural inclination is to not be too picky about the units and to feel like, well, centimeters squared, centimeters, it's the same thing. It's not the same thing. So even if you sort of like, personally feel that way as a teacher, as a math teacher, you need to make sure that you're really following through with that and that you're making sure that students are using the correct units. So for your checkpoint problem, so what would be the area of one side of the cube? We've already kind of worked through that. But what would be the volume? And so think about what the volume would be, and you could either think about it by counting, so doing it concretely. If you want to start thinking about how you would do that by a calculation, that's fine, but we're going to be coming to that a little bit later on in the section. Um, if that makes sense for you, then think about what the 4 by 4 by 4 cube would look like, or the 2 by 2 by 2 cube, or the 5 by 5 by 5 cube. And then eventually what we want to get to is the n by n by n cube. So what would happen in that general case? So a couple of ways to go with the checkpoint problem. Start by just looking at that 3 by 3 by 3 cube on the previous slide, and then extend that into 2, 4, 5, whatever. And then if you're really feeling bold, generalize it all the way out to the abstract, to the n by n by n cubed case. If you have any questions about that or anything else from the slides or from the section, by all means, please, as always, bring those questions to class and we'll get them answered. All right, thanks.